Hi, this is Big Tuition and this is a quick review for the chapter of differentiation. To start off with differentiation, I want to first do a short recap on what are functions. So, if you recall, functions are relations of two variables. They are mapping between one variable to another. And differentiation, when we differentiate the function, what we actually get is the rate of change. So when we write, we differentiate one with respect to another. So let's say differentiate y with respect to x. This is the notation for differentiating y with respect to x. What we're actually doing is we're finding the rate of change of y with respect to x. So as x change, how does y change? So in the context of A-level, most of the time we do pattern recognition and we just look at the patterns, and that gives us to all the derivatives. So after we differentiate a function, the result is the derivative. Okay? So here are all the common derivatives that are not found in MF26. Okay? It will be very helpful for you if you can memorize all this by heart. If you can't, you should try to at least remember as much as possible. Okay. Of course, this is the most basic one where we always start off with. So, for example, we can differentiate x squared, and we can see that the power n is being taken down and placed in front of x, and the power itself is subtracted. So, differentiation of x squared is 2x. In other words, derivative of x squared is 2x. There are some basic rules that you also need to remember. One is the chain rule. When we want to express the derivative of y against x in terms of another variable, for example u, we can actually write it as a chain rule. So the rate of change of y with respect to u multiplied with the rate of change of u with respect to x will give us the rate of change of y with respect to x. Okay, so when we have more than one variable inside a function that we want to differentiate, we will have to apply the product rule. Okay, so let's say we have two functions, u and v. When we try and differentiate uv, we can actually write it as u dv dx plus v du dx. Okay? And if we have a product rule, we will have a quotient rule where u and v are divided against each other instead. So in the case of a product rule, it doesn't matter which one you write at the start. You can write u dv dx plus v du dx or v du dx plus u dv dx. But in the case of a quotient rule, it's a bit more nuanced because you must start with v du dx minus u dv dx. If you flip around, then it won't be the same, right? Because you are subtracting a different number, and the denominator will become v squared. In actual fact, you should be able to get our quotient rule by taking 1 over v as v using the product rule. So for example, you can try and d dx u over v equals to d dx u 1 over v. And then you apply the product rule to u and 1 over v, you should be able to obtain the quotient rule. You can try this as a practice for algebraic manipulation. In any case, try to get used to all this, so when you apply it, it becomes second nature. Let's go through some of the common derivatives. So when we have so first we already talked about this basic one where we try to differentiate a polynomial term kn at kxn. But what if we are differentiating not a function of x to the power of n? Here we can apply chain rule. So d dx yn is equals to dy dy multiplied by dy dx. And this will be n minus 1 multiplied by dy dx. For sine and cosine, these are basically, just remember it, it's quite straightforward. When we differentiate cosine, there will be a negative sign outside. Given this, we can actually try and find why derivative of tangent x with respect to x is secant square x. So we can use quotient rule, right? Because tangent x is equals to sine x over cosine x. And with that, we can write dx sine x cosine x equals to cosine x cosine x, because v du dx, this is v du dx, minus this u dv dx. dv dx here is minus sine over v square, which is cosine square. The numerator is basically now cosine square x plus sine square x. It's plus because there's two minus signs, divided by cosine square x. And we know that by trigo identity or Pythagoras theorem, whichever you remember it as, this is the cosine square plus sine square equals 1. And this is cosine square x. 1 over cosine square, 1 over cosine is secant, and this is secant square. Okay? So for cotangent is equals to cosine over sine. So you can try to obtain this derivative on your own to practice your algebraic manipulation. Okay, moving on. Derivative of exponential is just the exponential. If there's any functions inside, the numbers will come out. So for example, dx e to the power of kx will be equals to k e to the power of kx. Okay, you can do this by chain rule. And derivative of ln x will be 1 over x. So for techniques, if the equation cannot be easily made into y equals to fx form, because previously we have always been just differentiating a single function, right? Like for example, sine x over cosine x, that's just a single function. If it cannot be easily made into a y equals to fx form, then it is possible to actually differentiate both sides with respect to x. So for example, y equals to sine xy, okay? It's much easier to see when you have an example. Here, it's difficult to make y the subject. And if we cannot make y the subject, it's a bit difficult to find out, to differentiate this, right? So what we can do is, if we cannot make y the subject, we just differentiate both sides with respect to x. So differentiating both sides with respect to x, we have dy dx on the left side equals to d dx sine xy. d dx sine xy is cosine. Okay. We can write properly, d sine xy dxy and dxy dx. This is equals to cosine xy multiplied by dx, which is just 1 times y, plus dy dx multiplied by x. From this step to this step, this is product rule. This is product rule, okay? This is chain rule. Okay, so next, all we need to do is do some algebraic manipulation to get to dy dx equals to cosine x y multiplied by y divided by 1 minus cosine xy. Okay, it takes a few steps between here and here. Try and work it out to see if you get the same answer. But here you see that we are able to obtain the derivative of y with respect to x without making y properly the subject. Alright, and next we have parametric equation where x and y may be related by a third variable, for example u. Here, as per the chain rule, we can get basically dy dx equals to dy du times du dx. So this is quite straightforward if they are related by a third variable. Okay? So for application of differentiation, there can be quite a few. Actually, differentiation is very important, especially when finding the maximum or minimum points of a graph. Because differentiation tells us the rate of change. So when the rate of change is 0, we know that it is probably a turning point. Okay, probably a maximum, minimum point, or an inflection. So here, we introduce the first derivative and second derivative test, which is here, first and second. So we see that when we have a graph like this, the derivative, which tells us the gradient, also the rate of change, they're all the same thing in this context. The derivative is first negative, then 0, then positive. That's a minimum point. In the case of a maximum point, the derivative is positive, 0, then negative. In the case of an inflection point, it will be positive, 0, then positive, or in the other case, because remember, there are two types of inflection point. In the other case, then the derivative will be negative, 0, and then negative again. Okay, so that's why there's two things here, because there can be two types of inflection points. In the case of a first derivative test, it will be very clear about whether if it is a minimum, maximum, or inflection point. How do you do the test? You will take, first you equate the derivative to 0, you locate where is the point of interest, where is this point, this point, this point, and this point. And then you add a small amount to it and substitute the x into the derivative. So for example, we know that dy dx equals to 0 at x equals to 0. Then we substitute dy dx x equals to 0.1, for example, and we check whether is it more than 0, less than 0, or equals to 0. Okay, most likely, okay, equals to 0 is quite rare unless it's a straight line. So most of the time it's more than or less than 0, and then we can start looking at the first derivative test. This method is a little bit more troublesome because now you have to substitute more values in, but it's the most conclusive one. The second method is also is more straightforward because when you differentiate twice, the minimum point could give you a positive second derivative or 0. The maximum point can give you a negative or 0. If the minimum point, if the graph gives you a positive second derivative test, okay, if the graph gives you a positive second derivative test, it is guaranteed to be the minimum point. If it gives you a negative second derivative test, it's guaranteed to be maximum. But if it's 0, then that is inconclusive because it could also be an inflection point. So second derivative test is usually faster because you can just differentiate straight away, find equal to 0, and usually when you differentiate, the function gets easier and easier. For example, the x square graph becomes x graph, then you differentiate again, it becomes a constant, right? Or x cubed becomes x squared, then becomes x graph, linear graph. So usually second derivative test is easier, but first derivative test is more conclusive. Okay, so that is probably the most important application of the differentiation. Another application is actually in the form of a Maclaurin series. Okay, Maclaurin series is a form of expansion. So it expands functions into a series, so it becomes easier to compute. In a sense, it's very similar to a binomial series, if you recall. A binomial series is when you have when you try to expand this kind of function. When we have 1 plus x to the power of n, the binomial series can be expanded as 1 plus nx plus so on and so forth. So in this case, we can actually calculate for it without actually expanding all the brackets fully. It takes very long to expand out to the power of n, right? When you have two terms in the bracket. So a binomial series assists us in representing a plus b to the power of n type of function. But binomial series does not work for functions like trigonometry, logarithm, and exponential. These functions are more, or rather you just can't write them in the binomial form. And that's when the Maclaurin series come into play, okay? So the Maclaurin series tells us that a function is equal to this expansion, the function with the 0 substituted in it, plus x times the derivative at 0, plus x squared of the second derivative at 0, and so on and so forth. Okay? So the conditions for Maclaurin series existing is that, first, the function must exist at 0. Because if the function does not exist at 0, then the whole thing the whole expansion doesn't work, right? The second thing is that the derivative must exist for all n. Because if any of the derivative does not exist, then again, your Maclaurin series will become undefined at some point. Thirdly, the derivative at 0 must be defined for all n. Okay? So this is different from the second condition. The second condition just tells you that it is differentiable. The third condition tells you that at 0, the nth derivative is not undefined. So these two are slightly different. There's a nuance, but it can be important. So if let's say I tell you that the derivative is 1 over x, but we know that 1 over x is undefined at 1 over x is a defined function, but it's undefined at x equals to 0. So then if one of the derivative is 1 over x, then this condition is not met. And fourthly, the series must converge to a function, fx, to the original function, So there must be so we notice that there's always an x squared, and so on and so forth, right? So if the derivative keep becoming larger and larger, there is a possibility that this function, this sum to infinity, does not converge, because we know that when we have x to the power of a very large number, it could easily end up becoming infinitely large. So to ensure that the series converge, sometimes we have to restrict the range of x such that this series expansion can converge to a real number, to a defined answer. So these are the conditions for Maclaurin series to exist. Quite important, should familiarize yourself with all this to make sure that when you do Maclaurin expansion, you don't end up expanding to the wrong thing. So for approximation, the Maclaurin series is very important for approximation because of how you see that you expand out to all these terms, right? Expand out to all these terms. It is useful when your x is small. It is useful when your x is small. Okay, let me write it down there. So we see that in this series, there is an increasing power of x. As there's an increasing power of x, it means that when x is small, the terms becomes quickly very small. For example, when x is 0.01, that means your first derivative at 0 is multiplied by 0.01. Your second derivative at x equals to 0 is multiplied by 0.0001. And the third derivative will be even smaller, right? So when x is small, this series will quickly approach 0 and will be very, very close to the function at 0. Therefore, when x is small, this series can be approximately calculated with only the first 2 or 3 terms of the Maclaurin series. So common approximations include like sine x equals to x, sine x equals to x, cosine x equals to 1 minus x squared, and tangent x equals to x. So these are the common approximations that you will need. For all approximation, there will definitely be an error. And so the error calculation is given by this. The percentage error is given by the actual value minus the approximated value by using something like maybe sine x equals to x and divided by the actual value. This is important. You must divide it by the actual value, not the approximate value. And the percentage error is this fraction multiplied by 100%. Okay, with that, we should have covered the content for differentiation and Maclaurin series. I hope this helped you for your revision. Happy studying!